Okay, thank you. And thanks, Heidi, again for your invitation. It's my pleasure to talk in Melbourne. And although I'm not physically there, and for those who didn't know me and history, and actually I stayed in Melbourne for 4.5 years to do my PhD at RMIT University. So today I'm also very pleasure to look at and to see a few friends like Michael and and Marcus, and so and also I'm very actually pleased to know and Melbourne has a large group or large number of people in AI machine learning. So today my talk would be actually evolutionary machine learning. So it's a combination of evolutionary computation and machine learning. And here I'm good. Let me see how I can do. Yeah. So I'm going to provide a very brief view for machine learning and evolutionary computation, and mainly very also briefly discuss the coverage. Today, I'm afraid couldn't go to the depth. That's if you go to depth, that would be a different talk. And this is very much overview in different aspects. And finally, I'm going to talk about some challenges and application. And these days, AI is hot again. And many people are claiming they are doing AI. And many people also claim actually AI is machine learning. Machine learning is deep learning. Deep learning means actually deep neural networks. And deep neural networks means deep convolutional neural networks. So basically, that has been mentioning again and again, partially because actually CNN, is very popular, particularly in, image analysis, signal processing, and natural language processing in those domains. And if we look at the major AI conferences, NIPS, ICML, IEEE, ITCVO, and so on, and also the major data mining conferences, and or if we look at the major journals and in AI, and including attribute transactional neural networks, or attribute transactional cybernetics, or evolutionary computation. And many of the major conferences, actually, they use CNN or variant and to solve problems, real-world problems. And accordingly, many people think in that way. And another major reason, I guess, would be the application people. They have been using CNN or variant, or and to do and to solve a particular task, and they think that's all AI and machine learning. And how about the normal people think? I mean, how about the traditional AI and machine learning people think? How the evolutionary computation people think? How about our operations research and optimization people think? Certainly, that we couldn't make this conclusion. AI or machine learning is simply CNN. But this reflects the fact that, and many people in the world from different particular application areas and use a kind of CNN or variant a lot. So what is machine learning? I guess, and AI and machine learning, these are very broad. Different people always have different opinions. The scope and would be different. And I guess this is the 5 tribes. And many, it's famous and, by and Pedro and Domingos, actually, this is a famous one. They roughly and split the machine learning fields into actually 5 subfields: symbolists and connectionists and evolutionists and Bayesian people and kernel-based method, basically. And the symbolic side, that still many people are doing that. Actually, before the 1990s, this area used to be dominate AI and machine learning. And later on, and in the 1980s, the neural network came, and basically a lot of different kind of techniques and based on gradient descent. Well, those techniques couldn't guarantee a global solution or the ideal solution or optimized solution, but can guarantee a satisfactory or can find a good solution, right? Here, and again, actually in the 1990s, there's a lot of progress, although it was born in the 1950s, 60s, but 1990s, there's a boom, right? And evolutionary computation or evolutionary and algorithms, that's a lot. And this has been a mainstream of machine learning, mathematics, or statistical probability-based, that's a lot of things. And here, the kernel-based method in the 1990s, that's probably a lot. That's a typical example would be actually support vector machines. So this, and I know many of the traditional people might not like actually those two. Previously, they don't like neural networks, don't like evolutionary computation. But these days, they can't ignore neural networks, right? The deep learning is so hot, but many people still don't like actually evolutionary. That my view is that no matter who or how people like or dislike, doesn't really matter. As long as they can solve real problems, particularly difficult problems, or some method can solve simple problems, and we should treat them actually as useful, as equally useful, right? And evolutionary computation, from the previous 5 trips, we know that evolutionary computation is one of the major paradigms in machine learning, although some people haven't recognized or don't want to recognize, right? The evolutionary computation actually itself is also a very big domain, and that's my own categorization. I split that into 2 big categories plus other, basically. So the first one is the evolutionary algorithms. That's like the traditional schemes like genetic algorithms, evolutionary strategy, or evolutionary programming. That in the 1950s, 1960s, already there. Actually, people from different areas independently developed that until the late 1980s. People find that actually they share the same or very similar ideas and using actually a population and candidate solutions and in the population multiple solutions, right? Also follow the Darwinian natural selection and gene theory, right? So, and of course, there's another one, genetic programming, and it was invented probably in the late 1970s, early 1980s. But John Koda, Stanford University, popularized it in the 1990s, right? So basically that's the population-based, that's based on Darwinian and natural selection gene theory. This group is also population-based, but actually called swarm intelligence. And typical examples would be particle swarm optimization, anti-colony optimization, and so on. And here, this is based on social intelligence. And so not necessarily Darwinian natural selection, but social. But a common characteristic is actually, the still population-based. And I have to, this is somehow, you might ask, what's the difference between evolutionary algorithms and swarm intelligence? And from actually intuitive point of view, I can say that evolutionary algorithms are based on human evolution. And swarm intelligence is probably based on animal evolution, like, some flies and, birds and all fish in the water, or ants, and or some other animals, actually, that's based on that. In fact, from algorithm and point of view, they also have distinguished features. Evolutionary algorithms, the population and the individual population in the population are not actually, are very independent. They are not actually connected, basically, if not doing crossover remutation via the genetic operators or some kind of evaluation, fitness evaluation. But the individuals in the population in small intelligence, actually, they are primarily naturally connected via some topology. So this is, you can see, there's a key difference from representations. They have key difference, right? So if any other algorithms, also population-based, but if they can't fit into evolutionary algorithms, all small intelligence, I put it other, okay? Typical examples would be, some of the evolutionary multi-objective organization, or you can say it can apply in all those early algorithms or mimetic computing. That's a lot of different kind of things. I have to highlight 2 points. And here, firstly, some people, including the big names in evolutionary computation, think actually evolutionary computation and it's actually evolutionary algorithms. Actually, our Carlos Qualo is I think it's a typical person, or Marco Dorigo. They think actually, and the evolutionary algorithm, that's evolutionary computation, but small intelligence, not evolutionary computation. I'm not sure if Carlos still keeps this view. At least several years ago, that's his view. But now he's the editor-in-chief on transactions, attribute transaction evolutionary computation. I guess, and he might or might not change his view so that evolutionary computation scope also includes small intelligence, right? But doesn't matter. I don't want to argue there. But mainly, this refers to a group of algorithms that's based on population, so multiple and solutions, candidate solutions there. So actually, that's currently the attribute transaction evolutionary computation journal use this definition. The AEs, associate editors, have discussed several times, and basically, I propose population-based. Majority of people and think that's covered almost everything, but our Hussein Abbas correctly identified couldn't cover something, only a single 1+1 or some of the and biological evolution couldn't cover that, but covered probably over 98% of the algorithms in this category. The second point I would like to highlight, traditionally, when we talk about evolutionary computation, people always mean evolutionary or optimization, but I would like to identify or want to point out that, in my view at least, evolutionary computation includes both evolutionary learning and evolutionary optimization. So, and of course, probably over 80% of the people and within evolutionary computation are doing optimization. Actually, among those people who are doing optimization, probably and over 70 or 80% of those people are doing numeric continuous optimization and working on some benchmarks, actually. So, but I'm saying here, EC should include both evolutionary optimization and evolutionary learning. Of course, and people might say that every learning would need to use optimization. I think I have to agree with this. And also, many of the optimization tasks also involve the learning, which is also true, right? So that's something I think, ACM has a special, has a new journal called ACM Transactions on evolutionary learning and optimization, covered both sides, okay? So it's interesting in this area. And now I come to the main topic today, evolutionary machine learning. And this actually, I guess, they have at least 2 categories or 2 different kinds of views. One narrow view and the other is a broad view. The narrow view means that, okay, and the evolutionary learning means actually the EC method used for machine learning directly, okay? And if we follow this narrow view, all the information, all the and evolutionary computation method or algorithm I mentioned here only actually probably genetic programming, learning classifier systems, and Michael is an expert here, and artificial immune systems. Probably also only those very small number of evolutionary algorithm or evolutionary computation algorithms belong to actually the narrow view of evolutionary learning, techniques. But I personally would like to take a broader view. The broader view means actually the narrow view plus actually any easy method I mentioned earlier, all those methods, and and it's doing any aspect of machine learning tasks, and including those automatically, basically find the entire model, including the model structure or architecture, plus coefficients or parameters, all. And if EC method is used to optimize the parameters or coefficients for some predefined models. From my point of view, actually, the evolutionary machine learning cover all those areas. Okay? And I guess our group probably wrote the first survey paper on evolutionary machine learning. That's actually immediately before COVID. And just a couple of months ago, actually more than a couple of months, right? Just published online, actually. Wolfgang's group, Wolfgang Wellington, and Amy is from UTS, actually, from our Australia and New Zealand, right? Australasia. So has a second survey, actually. It tends our previous survey, or from a different angle. Okay. Here, that's the survey paper published on the Journal of Rural Society of New Zealand. And actually, the follow-up, I don't know who wrote that, actually, is a newsletter, highlights how evolutionary machine learning is actually important for real-world applications. People can look at that later on. So here, this is a very extensive, actually, taxonomy for evolutionary machine learning. I take the broad view, actually, but today I'm going to only mention a few of them, or the main ones, right? The first one would be EC for classification and feature manipulation, or feature engineering these days, a fancy term, right? If we look at what EC methods used for classification or constructing classifiers automatically, and I have to say, actually, quite a different methods. As I mentioned, GP and LCS or artificial immune systems, those three methods can construct the whole classifier, including the model structure and coefficients simultaneously. They can do that automatically. But the majority of other EC methods, like genetic algorithms or particle swarm optimization, you have predefined model, you use a classifier, or like linear discriminant analysis. And then the task for the EC method is just to try to learn or optimize, today that's the optimization group, right? Optimize those coefficients. So, and this is mainly used actually a lot of very broad usage here. And that includes not only the normal classification, but also classification with class imbalance problem, unbalanced data. Right? One or minority class, and often the important class, only has a very small number of instances, while the other majority class majority class has a huge number of instances, and class imbalance problem. And like the medical domain and the legal domain often has that issue. Right? And also many of the feature values are missing values or incomplete data, and imputation, and try to using some method. EC method can also do an imputation, impute those missing values first, and then using the normal machine learning technique to do. And the EC method can also do actually the imputation or actually and classification directly and automatically. Okay, this is a big area. I'm not going to go any detail than that. The next one also, when we using actually and for classification, and then feature selection and feature construction cannot be omitted. Okay, and the EC method has been used for feature selection and feature construction for quite a few years, for a long time, and now the EC method has become a major stream for feature selection. And Bill's early survey paper, and now has over thousands and hundreds and citations there actually. So in terms of the paradigms, EC paradigms, and then we would have, and all those areas, evolutionary algorithm, swarm intelligence, and other areas they used for feature selection. In terms of the evaluation method, that can be categorized filter-based method. Don't wrap any classifier or machine learning method, standard machine learning method, but only use some simple statistical or information theory measures. And so don't wrap classifier filter, right? But often get more generalized feature set, subset. Wrap approaches is very simple. It's just wrap a machine learning algorithm or a classifier for evaluation, to evaluate the goodness of subset of features, some combined approaches. And also in terms of filter approaches, you have, as I mentioned, information theory measures, correlation measures, distance measures, many of those actually, and that's all actually have been used for actually and within actually evolutionary computation method and all algorithm for feature selection. So the next topic in actually the machine learning task is regression. It's actually the AI people would like more probably think that the classification is dominating. But if you ask our colleagues in statistics or operations research, they might think actually regressions is more popular than classification. So for continuous and the output is a continuous number or real number or discrete or nominal categorization, right? So that's different. But again, EC method have been used in different areas, including parameter optimization. Again, actually, you use some predefined actually regression models and like linear or some kernels or others. But the EC role, the role of the EC algorithms is just optimize the parameter values or coefficient. And so that's parameter and the estimation. And also, if you have a number of methods, you want to make a selection and then model selection and genetic algorithms and particle swarm optimization, ODE, differential evaluation, can do very well. But if you want to actually say in many real world these days, big data era, right? The data are often very complex, very big, right? And thus, it's very hard, even for statisticians, to find a single distribution. So all this data belong to a particular distribution. And then we can choose the regression model and the task become, just optimize the coefficients or parameter values. However, the big data era, it is very hard to find the distribution of the data. In many cases, the data might belong to multiple models, multi-model program, or multiple distributions. Using the traditional statistical method might not work. In this case, genetic programming, or actually this is a typical method they call it symbolic regression, can automatically learn the model structure and coefficient simultaneously. Okay, and of course, learning classifier systems and artificial immune system can also do that. Right? And also, that Qi Chen is one of my previous PhD students. Now she's a staff member here, and she actually used that actually embed structural risk minimization actually put into the genetic programming for symbolic regression, and the referee liked that very much. Say, the structural risk optimization and minimization, used in statistical learning theory, basically the pack learning, probably approximately correct theory, right? A typical and stream is VC dimension. V and C are two Russian scientists, right? So use that. They have produced many hundreds of PhDs, but they are seldomly practically usable. And Qi might be one of the very early, at least in Evolutionary computation in genetic programming domain, probably the first person, and who made this theory with the dimension practically usable, not only theoretically usable. Right? Another point, actually, another aspect is the easy factor method for clustering. We all know that clustering is very similar to classification. And the only difference, or the major difference, is actually they don't know the class label, don't know the output, the desired output, right? And many EC methods has also been applied to both actually fixed clustering and automatic clustering. The fixed clustering means, although you don't know the label of class label, output label, but you know the number of clusters, and k-mean is a typical example of this kind. And some other methods, my other clustering method, you don't really know the clusters, number of clusters in advance. And the EC methods have been used in both scenarios. In particular here show you actually GP how genetic programming is doing and the clustering, and in different generations, iterations, doing better and better. Particularly visualization actually can do well. In the traditional clustering method, usually you just is embedding approach, right? So basically, we have a group of data. You apply a clustering method and do the clustering and then get the result. If some new data came, we have to start from scratch and doing that embedded. So, but genetic programming recently, and my previous student, again, he's a staff member here, and he's using genetic programming to learn a model like mapping, that can actually not only do on the existing data, but for future data, he can also actually learn the model just like supervised learning and to do clustering. It's kind of classification. And here, but there's another key difference between GP clustering and traditional clustering. Here, the model actually you can see that have two traits can do that clustering. You can interpret what happened there. So this actually paper received best paper award in EuroGP. Actually, it's a flagship conference in genetic programming. The next field actually is in evolutionary computation, has been used for computer vision and image analysis. That includes a lot of different kind of tasks: edge detection, segmentation, transformation, and object classification, detection, tracking, a lot. And of course, also feature and selection and feature construction. And I'll give some examples later on. And recently, my students published a book for genetic programming for image classification here by Zhang. The next task, actually, EC has been used for scheduling, routing, and combinatorial optimization, right? This, this different kind of this scheduling, this routing problems, and, supply chain or logistic regression, and class scheduling problems, okay? And again, actually, there's a lot of areas, including those, scheduling and bin packaging, web service, resource allocation, and, that's different method. But it has actually and static scheduling, and majority of the current methods are doing that. And also have dynamic scheduling. Dynamic scheduling, many people are doing that, trying to using window approach or other approaches, rescheduling approach, so convert dynamic problems to static problems. But actually, EC method can be used as a hyperheuristic approach. Hyperheuristic is just a machine learning approach, actually, and that can do automatic and heuristic selection and heuristic construction. The Nottingham group and Edmund Burke, that is leading this area. But if for EC algorithms, for using as a hyperheuristic approach to automatically learn and optimize scheduling rules, actually, we are actually one of the major research groups doing this. This is actually my postdoc or previous PhD students, and she published a book, and in this area, and early this year, and her PhD thesis, she finished PhD thesis last year, also this year, and got the ACM SIG and best PhD dissertation, and it's like a honorary mention, it's like a run-up this year. So as I mentioned earlier, if we talk about machine learning, if we don't mention deep learning, that means many people think you didn't do any kind of AI or machine learning. So we have to mention this. But EC method has also been used for deep learning, okay? But what is deep learning? Different people have different opinions. And what the one I like is Professor Zhihua Zhou. His definition, he visited here and in 2017, 2018 actually, and he was the program chair for EGCAI when PreCAI was held, EGCAI was held in Melbourne in 2017. Actually. So I went there, many people here, I believe also there. And it mentions that actually, as long as learning algorithm meets three requirements, say layer by layer processing and feature transformation, and then the model need to be sufficiently complex and to eat actually a lot of big data. And these areas would be, fixed this aspect would be deep learning algorithms. From that point of view, actually deep learning algorithms I categorize, I said, many people think deep learning are deep neural networks. There's no doubt neural networks are leading this area, that I don't have doubt. But that doesn't mean no other techniques are also deep learning, right? The neural network based that including feedforward recurrence, including convolutional belief networks or autoencoder or long short-term memory or many other things that's neural network based, right? But that's also some non-neural network deep learning method, like the DeepFirst that's published in EGCAI 2017 in Melbourne, and also deep PCA and also deep genetic programming approach. And wait a moment, I'll also show some examples of that, okay? And I have to say, I use the term evolutionary deep learning, and so that's, but that's something many years ago, but I didn't insist. I tell you a story later on. But mainly the neural network based, no doubt they are dominating that. There's no doubt. But they clearly have some disadvantages. And one is, too many parameters, thousands of layers. Now, let's not talk about thousands of, even hundreds of layers. AlphaGo, many other things these days, we have thousands of layers, even hundreds of layers. We can't really understand. And the gradient descent algorithm, and cannot guarantee global optima. And to train such large network, the big training data is really needed. But in many real-world applications, like in health or medical domain or the legal domain, we don't really have so many instances. People, countries like USA, China, or India, they have a large population, and countries like New Zealand, probably to lesser extent Australia, and the number of population, the size of population is not huge. And if you want to get so many, and in particular disease like cancer or particular cancer, probably the examples not that great. So the deep neural network are not necessarily good. And if you have a big model overfitting will occur. Of course, theoretical analysis is difficult, and very much black box is very hard to interpret. Having said that, majority of the big deep neural network models, ResNet, DesNet, VGG, many of them are manually designed, I have to say. And the question is, the manual design, they use some group of people, a group of people with expertise in deep neural network, in neural networks, a group of people with expertise in a particular domain and application domain. And then those people work together and then figure out some deep model and then send to hundreds of thousands of GPU servers. And then overnight they get a result. And then trial and error may do a lot of time, many days. And then when they publish, they only report the final architecture, the final model, and the best the best accuracy on very large data sets. They didn't report how they did and the process, how many people they use. They never report that, actually. So the question is, can we automate that process, the learning process, the architecture of neural networks, the parameter values, and the hyperparameters, and the layers of the normal parameters, and the weights, right? And yes, we can. And then that's many methods have been proposed. In general, we have at least 3 big categories of the method that can do actually deep learning and can help automate design of deep learning models. And one category is reinforcement learning. Second category was evolutionary learning, evolutionary computation. Third one, actually very recent in EasyCat, Triple AI, SML, the Bayesian methods or gradient-based method. And I have to say, those methods, Bayesian or gradient-based method, haven't achieved competitive result as easy method and reinforcement learning, actually. And they are, training is efficient. It has used fewer GPU hours or GPU days, but the accuracy is not good enough. Okay? And easy methods is a bit expensive, but deeper reinforcement learning even more expensive than the easy method. But today, I'm going to say, that's code actually using easy methods to automate the design of deep learning models. And so I call it evolutionary deep learning. Evolutionary deep learning actually I categorize as 3 stages. The first stage, typical example would be Professor Xin Yao's survey paper and IEEE proceedings of IEEE in 1999. So using EC methods at that time, mainly genetic algorithms, and can be used to evolve either the and neural network architecture all the weight over combination. Okay, but at that time, the neural networks is talking about 3 or 4 layers, very simple neural networks. And then after in the 2000, the first 10 years of 2000, a typical example would be NEAT, or actually variant of NEAT. The people would be Risto and Ken, actually Ken Stanley or Risto, actually. They actually say neural evolution, and extend the network would be much deeper, but not as 100 layers, and probably like as 5 or 7 or 8 layers or around 10 layers later on. And until actually the recent 5 to 10 years, less than 10 years, 5 to 7 years probably, typically after 2015, that's become the third stage, and then would be much deeper. The number of layers is much more and come to 100. Okay. So evolutionary deep learning, actually, I also categorize, as two, at least in 2 categories. One is still neural network based, and this area, and Risto and Ken would like to call it deep neural evolution. This is the name used in Gecko at the track. Okay. My term is evolutionary deep learning. I proposed this term actually in 2012 or 2013. And then many people disagree with this term, including people in my group, and people know Will and Bing actually. They think actually I shouldn't make up terms actually there. And then I was not confident enough at that time. I withdraw my claims. But until 2015, but still before AlphaGo was born, and I found actually we should really call it evolutionary deep learning actually. And now the first term probably evolutionary deep learning. This is the term proposed by me, but I talk a lot of time. The first publication probably in 2018. I also deliver a plenary talk on Wiki 2018 in Brazil. Actually, that's since then, and many survey papers, and in this domain, Obama, they have been using evolutionary deep learning. So there's no doubt neural network-based deep learning and evolutionary deep learning still dominating. A typical example would be actually neural architecture search. But also we have the evolutionary deep learning that focus on hyperparameter or some parameter search, also including actually those on the transfer function or activation function a lot. And also many of the methods, ED methods, have been used there. With a moment, I'll give you 1 or 2 examples. And also another one, as I mentioned, mentioned, from 2012 or 2013, and many fields actually, in this field, people started doing this. With a moment, and I'll give you some examples. And in the year 2018, 2019, Risto claimed that in the SIG evolution newsletter called EC is actually deep learning. He has a lot of argument there, and now some people disagree again. But I thought, given that the lesson I said people should not deny immediately. Let's evolve, the evolution computer, let's evolve a few years. Let's see whether this is true or not, right? So this is actually very first of deep neural networks we automatically learned from my group, and Dr. Yang Sun, and now he was my postdoc, and started from 2017, and this work was done 2017, but until 2020, it's formally published. Actually, many rounds of review, and also, it's a bit slow. This actually got almost 400 citations, and very recent years, and it's a kind of highly cited papers, and people can have a look. I realize the timing is an issue, And this is the second piece of work. And we successfully used not only the, from scratch, but also use some of the blocks in ResNet and DeathNet, and then use this published on attribute transactions on neural networks. And also highly cited papers achieved and better results than the state-of-art results. All the manually designed methods, all the automatic methods are competitive to use a combination of manual design and expertise, human expertise, and automatic. Right? This is actually genetic programming-based deep learning. This is the kind of thing, and you can see that you can automatically do actually feature, so region detection and feature extraction, and then feature selection, construction, and classification. More importantly, the model learns and we can interpret. And I'm going to skip those slides. And I would like to say, using automatically EC methods, you can see automatically for feature construction, and then you can see this is MNIST variance data set, and using GP actually did very well for visualization and clustering. Okay, here is the model for used for this ensemble learning, not only feature learning automatically from the low levels, but also the ensemble learning. Ensemble, we can see that in this example, and GP can automatically learn different kind of classifiers. Here, all the ERF, in fact, this is actually the GPO automatically constructs features, and then automatically form ensemble. We do not need to determine or predefine the number of base classifiers, but can do that automatically, and can automatically choose either existing classifier, base classifier, or automatically learned classifier. Actually performs very well. I think to wrap up, and I mentioned a few aspects using evolutionary computation and to help machine learning, but haven't got any time to mention those areas. And also a lot of areas, evolutionary transfer learning and automatic machine learning actually play, ECs are playing significant roles. Having said that, and have a lot of challenges and current issues, those scalability, generalization, interpretability, still theoretical foundations, and also have used for many different real-world applications. Okay, and that's something. And I think I need to stop here, but allow me to give one more minute. And Michael says, and our group is growing. Yes, and we have 20 academic staff members at the beginning of this year, but we just 3 new staff members arrived. We have a number of postdocs and some bigger AI from other staff members, and also many actually over 50 PhD students. So I'm going to and I think and basically stop here. But finally, I would like actually thanks Heidi and Charlotte for this invitation. Charlotte unfortunately is in Europe, and the timing is exactly over date actually. Can't be here. And of course, this is not only my own work. There's many and represents the work for many other people actually in the group, and also supported by many different kinds of research grants. I would like to stop here and happy to answer questions. I know I used a little bit more than actually almost exactly 50 minutes. And yeah, I planned 45 minutes. Anyway, thank you.